So just a quick recap of what we did in the first lecture. So we looked at, first of all, the irrational rotation on the circle. We saw this was minimal, meaning all orbits are dense. Then we looked at this expanding map on the circle, z goes to z squared. So we saw this was better in the sense it was topologically mixing and periodic orbits were dense. Then we looked at our first example in continuous time. So a linear flow of translations on the torus with a given direction vector omega, and we saw that if the slope of the vector omega, this number alpha, was irrational, then this flow was also minimal. So every orbit for the flow was dense. And using this, we looked at what are called hyperbolic linear maps of the torus. So that means you take a 2 by 2 matrix with determinant 1 and integer entries. So this defines a map of the torus. X mod Z2 goes to AX mod Z2. Right. This is well defined because if you change X by an integer vector, then AX will also change by an integer vector because A has integer entries. So we assume that this linear map is hyperbolic. That means it's diagonalizable and both the eigenvalues have modulus different from 1. So since the determinant is 1, the product of the eigenvalues is 1. So 1 has to be smaller than 1 and 1 has to be larger than 1. And if you look at the corresponding eigenvectors, then if you look at in R2, if you look at the families of lines parallel to one eigenvector, that gives you a foliation of R2 which is invariant under the linear map. Right? The linear map is going to send a line parallel to an eigenvector to another line parallel to the eigenvector. And similarly for the other eigenvector. So you get two transverse foliations, which when you come down to the quotient, they give you two transverse foliations of the torus. On one of them, the one with eigenvalue less than 1, the map contracts along leaves of the foliation. That's called the stable foliation. And on the other, it expands. So I should have said this yesterday. So if we denote the stable foliation by Ws, and then Wsp is going to denote the leaf of this foliation passing through the point P. So 2 points xy, one can show that 2 points belong to the same leaf if and only if the distance between, so let me just call the map A again, A power nx, A power ny goes to 0 as n goes to plus infinity. Okay. So you can use this in fact to define the stable foliation, the leaves of the stable foliation. 2 points are in the same leaf if and only if the distance between them tends to 0 in positive time. And similarly, 2 points are in the same leaf of the unstable foliation. So I'll denote that by Wu. If and only if the distance between them goes to 0 when you iterate in negative time, as n goes to minus infinity. So we saw last time that this map was topologically mixing because you take any open set, then it's going to contain a small piece of unstable manifold. So when you iterate, that small segment is going to become longer and longer. And we know that every leaf of the unstable foliation is dense because it has irrational slope. So using this third example, and so therefore, when you iterate long enough, then the image of the small part of leaf will become a long part of leaf, which will become dense in the toes. So it's going to intersect every other organism.
Why do you need the stable foliation here? I mean,
Yes.
to prove it is mixing, then I can just say one eigenvalue is greater than one and the other is, okay, I see. So,
Well, the one reason why it's a valid question. You can take something in GL2Z.
Right, yeah.
You can take something in GL2Z. So in that case, also you will have mixing.
I see.
So
okay.
yeah,
Okay.
that works. So for example, you could just take the map x goes to 2x in the toes. That will be better. What is different? So this is what we're going to talk about today. Is that when the determinant is 1, then the map is measure preserved.
I see.
It preserves Lebesgue
I see.
measure.
I see.
Yeah. So this becomes important because today we're going to talk about measure preserving systems. So let me give you the definition. So you have x, b, mu. This is a probability space. So B is some sigma algebra of sets on X. Mu is a probability measure. That means it has total mass 1. And then T from X to X, a measurable map. So remember, measurable means for any set in the sigma algebra B, the inverse image is also in the sigma algebra B. So this is called measure preserving. I'll just write MP for short in future. So when you have a measurable map from a probability space to another measure space, you can always push forward the measure. Right? So measures push forward. So T star of mu, this is the push forward of mu, is equal to mu. So what that means, remember how the push forward is defined? That means for all elements of the sigma algebra B. So the measure of the push forward of A is defined to be mu of T inverse A. So what we require is that mu of T inverse A is the same as mu of A for all measurable sets A. Okay. So be careful. The correct definition is with the inverse image, not the forward image. You might think the definition should be mu of TA is equal to mu of A. That's not the correct definition. Because, the problem is if you try to define a measure by mu of A goes to mu of TA, that's not a measure in general. Unless the map is injective, that will not be a measure. It's not additive on disjoint. So some examples. In fact, all the examples we've looked at here, so if we call this 1, 2, 3, 4, then all of these are measure preserved. So the examples are 1 to 4. So you might think for the second example, well, if I take a small interval here, right, then its forward image is going to be an interval of twice the length. So when you apply in forward time, it doesn't preserve the measure, right? The measure doubles. But that's not the definition we're taking. We have to look at the inverse image. So here if I take a little interval of length L, its inverse image is going to be 2 intervals of length half L. Right? So half L plus half L is L. So it's measure preserved. The point is we look at inverse images, not forward images. Is this? So
in forward image, there is one more problem. If A is measurable, we can't say T of A is measurable.
we cannot say T of A is measurable. That's also. Oh. remember, the natural thing for measures is to push forward measures. Measures push forward, they're what are called covariant, whereas things like differential forms and functions pull back. Alright, so the first theorem about measure preserving transformations goes back to Poincaré. So this is called the Poincaré recurrence theorem. So Poincaré came up with this when he was working on celestial mechanics. So it states the following. So suppose t from x to x is measure preserving. X is going to be a probability space. Then for all measurable sets B, we can say that almost every point in A returns to A infinitely often. That means t power n of x belongs to A for infinitely many n greater than 2. So let's do the proof quickly. So if you have, just let's see what this is saying. You have some measure space, so you take some measurable set, then almost every point in this measurable set is going to return infinitely many times to this same measurable set. So it's going to recur. So you think of A as a very small set typically. Think of A as a small ball. So the proof is a sort of pigeonhole principle for measurable sets. Let me explain. So you're given this set A. So let's look at, so for an integer capital N, let's look at this set Bn. This is going to be the set of points in A which do not return to A after time capital N. So t power n of x does not belong to A for all little n greater than or equal to capital N. Okay. Now it's clear that if x belongs to this set Bn, then clearly t power n of x by definition does not belong to A, so therefore t power n of x does not belong to Bn, right? Because Bn is a subset of A. And this is true if I take any actually time bigger than capital N. So let me take a time k times n, where k is a positive integer. So what does this mean? This means that the inverse image t power minus kn of this set Bn is disjoint from Bn for all k greater than or equal to. Right? If you are in Bn, then t power kn of x is not in Bn. That means x is not in t power minus kn of Bn. So if I apply t power minus some k prime of n to this equality, it follows easily from this that actually all the sets t power minus kn Bn and t power minus l n Bn, these are also going to be disjoint for all k l greater than or equal to 1, k not equal to L. Right? Just apply t power minus some Pn to this equality. Is this clear? So all these sets are disjoint, but now T is measure preserving. So that means all of these sets have the same measure. So that means you've got...
Don't we need k plus L or something?
No.
It can be k is equal to L is equal to 1.
No, k not equal to L. It's an easy thing. Look, just apply T inverse once, right? Then you'll get minus k plus 1 and minus 1 here. Just apply some minus p, so you'll get minus k and minus k plus p, or whatever, minus k plus p and minus p. So that's it. So, I mean, in k and L, one of the two is going to be larger. So one you can write as k plus p, and the other you can write as k. So it's an easy thing. Okay, so all these sets are disjoint, but now this is the sort of pigeonhole principle. All of them have the same measure. So therefore, you have a bunch of infinite sequence of pairwise disjoint sets, all of these sets. So then all of them have to have measure 0, because the total mass is 1, right? So so 1 is the total mass. So this is greater than or equal to the measure of the disjoint union. K goes from 0 to infinity, 1 to t power minus k and p. So this is a disjoint union, so this is sum over k, measure of t power minus k and pn. And t is measure preserving, so therefore all of these have the same mass. We are taking inverse images. So this is the sum of just measure of Bn. So this implies measure of Bn is 0 for all n greater than or equal to 1, and therefore the measure of the union over n of Bn is 0. And now if you take anything which is outside the union of the Bn's, then you can see it's going to land in A infinitely often. Its orbit is going to be A. So if x belongs to A minus the union of these Bn's, what does this mean? This means that you're not in Bn, so therefore you're not in any Bn, so therefore given any capital N, there exists a little n bigger than capital N, such that t power n of x belongs to A. So that's it.
So did we take A of 1 and measure?
No. I just say, I mean, in practice you would, but this statement makes sense. This means that almost every x in A, you understand what that means, right? That means a set in A whose complement in A has measure 0. So if A has measure 0, then it's trivially true. So, yeah. So if x belongs here, this implies for all n greater than or equal to 1, there exists little n greater than or equal to n, such that t power n x. Okay, is this clear? Yeah.
Which part of the assumptions tells you that mu x is 1?
It's a probability space.
So why do you consider a probability space when can't we taking finite measure or something?
No, this is obviously false in infinite
Yeah.
measure. So you
so
need finite measures.
So can we apply like a Borel cantilever? It seems like it's okay.
No,
They
that's
have-
different.
It says that if something
Yeah, that's
occurs
right.
infinitely often,
Infinitely
it
often
seems
it's-
something like that.
Yeah, yeah. Well, this is the thing.
So is there any way to measure that how frequently they are?
No, the point is, I mean, so this is the famous example which is given to in most classes when people teach Poincaré recurrence. They say, imagine a gas in a box and you keep, first you have a barrier in the box halfway through, right? And you have your gas there. You know that if you lift the barrier, if you shift the barrier, the gas is going to diffuse and occupy the whole box. Now the movement of particles in the box is given by a Hamiltonian system. So it preserves a certain measure called Liouville measure, and that measure is finite because you're in a compact box. And so the Poincaré recurrence will tell you that even if you start with all the particles in half the box, you know that at some time it's going to return close to that initial configuration. So the gas, even if it diffuses to the whole box, at some time it has to come back to being in half the box, which you never see that. That means that time has to be very, very, very large. Okay. Yeah, there are estimates of recurrence for certain times of recurrence for certain systems. There are estimates. For, I guess for geodesic flows, you could say the recurrence times, yeah, you need something called exponential mixing. So I won't talk about that in these lectures, but exponential mixing will give you linear recurrence times, like an arithmetic progression of recurrence times. Okay, so let's do a of this proposition for our hyperbolic linear map A from the torus to the torus. That's our example 4. Periodic points are dense. So periodic, I'll just write periodic ordinals. So, for the proof of this, what you do is, so you have some small open set, and you want to find the periodic point inside this open set. Okay. So this open set is going to contain a small rectangle with sides parallel to the stable and unstable foliations. So take such a small rectangle. What we are going to do, so this is going to be our rectangle. Alright, I've magnified it. So we are going to find a periodic point for the map A inside this rectangle. So how do we do that? Well, the first step is, if I choose a point which is in the center of the rectangle P, and I choose a small ball, so that the diameter of this ball is much smaller than the diameter of the rectangle. Okay, so choose. So let's give names. So U is small rectangle. Small rectangle with sides parallel to stable and unstable foliations. So P is in U, let's say it's the center of the rectangle, and we choose a delta which is very small compared to the diameter of U. So this is my ball of radius delta. Then first of all note, like we said, because this map has determinant 1, remember, for a linear map, the determinant gives you the volume distortion of Lebesgue measure. Right? So, since this has determinant 1, it is measure preserving. So, by Poincaré recurrence theorem, we know that there is going to be a point Q in this rectangle, so that T power n of Q also comes in this ball, so that T power n of Q also comes back to this ball. Okay, so by Poincaré, there exists Q in the ball of radius delta around P such that T power n of Q also belongs to this ball. Okay. Now what we can do is the following. So let me introduce some notation. This will be useful later on. So if I have 2 points x and y, then I'm going to denote by, well, what I can do is I can follow the, say the stable leaf of x. So this is Ws x, and let me put a sub u to mean that I'm only taking the connected component of the leaf in u containing x. Okay, this leaf is going to, if I extend the leaf, it's going to keep passing through the rectangle infinitely often because I know the leaf is dense. So I'm just taking the connected component containing x. So that I'll denote W as ux. Then similarly I can look at the unstable leaf through y. So W u sub u y. This, they are going to have a unique point of intersection. So that we will call xy, square brackets x comma y. So this will be the unique point of intersection of the stable leaf of x together with the unstable leaf of y. Okay. So this point. Now I can do the following. So I have my rectangle U and I have my point Q which is near the center, which comes back close. So here is say T power n of Q. So I can define a map which is going to go from the stable leaf of Q. So I'm not going to take all of the stable leaf, I'll just take an epsilon segment, a segment of length epsilon around Q. Okay. And I can define a map which goes from this small segment of stable leaf to itself. What do? I take a point, say R here. Okay, take a point R on the stable leaf. Now you know that R and Q lie on the same stable leaf. So therefore, if I look at T power n of R, that's going to lie on the same stable leaf as T power n of Q. Okay, and I know that on the stable leaf, T power n is going to contract the distances. So T power n of R is going to be very close to T power n of Q. In particular, it's going to be inside this rectangle U, and so this intersection point of the unstable leaf with this stable leaf is well defined. So my map is going to be R maps to Q square brackets Q comma T power n R. Okay. Now this is what? This is a map from an interval into itself, right? So by Brouwer fixed point theorem, well, not Brouwer fixed point, this is for an interval. In higher dimensions you would use Brouwer, but here it's just for an interval. This is basic mean intermediate value theorem. You know this is going to have a fixed point, right? So this is a map from an interval to itself. So this is a self map of an interval. So this implies, so let's call this map phi. Phi has a fixed point. So what does that give us? Say R. This is in the stable leaf of Q.
Sir,
Yes.
the codomain of phi, I could see it as WS sub U Q, but
Right. Why is it inside the same interval? Yeah, good question. The reason is because, so here's my epsilon. I'll choose epsilon somewhat larger than delta.
So it's not just
Okay.
some small epsilon, but
No, it's a bit larger than delta.
clever.
Yeah. Yes, not too clever, but
Not too
clever enough. Maybe 2 delta would be good enough. Yeah, epsilon equal to 2 delta. Or 10 delta, if you want to be safe. 10
Then
delta would
it
be
shouldn't go out of the rectangle.
It shouldn't go out of the delta is very small compared to the rectangle. So then because the point is that t power n of q comes back close. So for t power n of q, I know that this map,
Yeah.
the intersection point is close to q.
Yes.
Right? So if I take anything here, n I can choose large, so that the contraction factor is very large. So then t power n of r is going to be very close to t power n of q because they're on the same stable leaf. So then if t power n of q, the intersection point is close, then also for t power n of r, the intersection point is close. So therefore it's going to lie in this interval. But that's a good question. Why is it like that? So what do we get? We get that r is equal to square brackets q t power n of r. That means that r belongs to the unstable leaf of t power n of r. Okay, so now the picture is you have some point r, which is again near the center of the rectangle, and t power n of r is close by, and it's on the same, these are on the same unstable leaf, right? That's what it means to be a fixed point of this map, because you're taking intersection with the unstable leaf. So something which comes back to the same unstable leaf. So now you're almost done, because what you can do is take an interval around t power n of r in this unstable leaf and apply t power minus n. T is invertible, so you can apply t power minus n. That's going to send this big interval to a small interval around r, because t power minus n is contracted. Where on the unstable leaf, there t power minus n contracts. So therefore again you get a self map of an interval, right? So if you look at t power minus n, so this is going to go from where? From some some cleverly chosen segment w in the unstable leaf, right? Unstable leaf around t power n of r. It's going to go into itself. And this guy again has a fixed point. This has a fixed point. That means t power minus n of some. So we've used PQR. What's left? X. So t power minus n of x is equal. So that gives our period. Is this clear? Yeah, and the x is inside this rectangle. So periodic orbits are dense. Okay, so now I want to come to the other main topic of today, which what's called ergodicity. So this is for measure preserving systems. So definition. So throughout our probability space, our measure spaces are always probability spaces. Total mass 1 throughout. So T from x to x, measure preserving, is ergodic So before writing the definition, I should give you an idea what it says. Ergodicity of a measure preserving system is something like irreducibility of the system. What it means is that there are no non-trivial invariant measurable subsets. Okay, that means you have your system, you cannot find a smaller measurable subset which is invariant. So it's, in that sense it's irreducible. So the formal definition is if you have a invariant set, so again invariant, be careful, does not mean forward invariant, it means backward invariant. So T inverse A equal to A implies the measure of A is 0 or 1. So you have no non-trivial invariant sets. So if it was not ergodic, that would mean that there is some measure, some set of measure, let's say half, which is invariant. So you could restrict to that smaller set. Here you cannot restrict to any smaller non-trivial set. Okay. Is this one? So yeah, so we can prove a simple result to start off, which says the following. So suppose proposition so if X is a second countable topological space and the measure mu has full support. So full support means that every open set, non-empty open set has positive measure. So mu of U is positive for all U open non-empty. And suppose we have T which is measure preserving and ergodic. Then so as we will see, ergodic, another way to think of it is it's a sort of measurable version of topological transitivity. So in fact ergodic in this case, as this proposition says, it will imply topological transitivity. It implies something stronger. Then for almost every x in X, the orbit of X is dense. So almost every point has a dense orbit. So in particular, it's topologically transitive. So what's the proof? Right. Okay. So let's do the following first. So suppose we take a measurable set of positive measure. Okay? Then I want to look at, like we did in Poincaré recurrence, the set of points which move into A infinitely often. So what we're going to do is look at let's say B sub n, again n is an integer, be the union for little n greater than or equal to n of t power minus n of A. Okay. So then the measure of these sets is of course greater than or equal to the measure of t power minus capital N of A, and the measure of this set is the same as the measure of A. So all of these sets have measure bounded below by a fixed positive constant, measure of A. So now if we want an invariant set, we take the intersection of these bn's. So let A tilde be the intersection over n capital N of Bn. Okay. So notice that this A tilde is invariant. This you can see. It's not hard to see. This A tilde is going to be invariant. Because what happens when you take an inverse image of a Bn, then you get basically the union of the inverse images from n plus 1 to infinity. But then you're taking the intersection over all n. So that will give you something invariant. So we've constructed an invariant set A tilde starting from the set A. But the point is T is ergodic, so A tilde has to have measure either 0 or 1. But now A tilde, we know that the measure is going to be positive actually, because this measure of A tilde, notice these sets Bn are decreasing, right? So by continuity of measure, this is going to be the limit n goes to infinity measure of Bn. But all the Bn's have measure bounded below by a fixed constant, mu of A. So the limit is also greater than or equal to mu of A, which is positive. So thus T ergodic implies measure of A tilde is 1 whenever you take A such that mu of A is positive. Okay. So now what we can do is take a countable basis for the topology, say UNs. So let UN be countable basis for topology. So then measure of each UN by hypothesis, every non-empty open set has positive measure. So this implies if I apply this construction, this measure of UN tilde will be 1 for all n. Therefore, if I have a countable family of sets of measure 1, the intersection is also going to have measure 1. So measure of intersection over n UN tilde is 1. But if x belongs to the intersection over n UN tilde, what does this mean? This means x belongs to UN tilde for all n. But belonging to UN tilde means what? So then UN tilde is again an intersection of sets. The notation gets bad at this point. UN sub n, what is it? So it's an intersection of these sets. So these were, so this means for all n greater than or equal to 1, you belong to one of these sets. Belonging to this set means you belong to a union. So union means there exists an n greater than or equal to n. Oh, I'm using too many n's. Let me change u to k, the subscript to k. K. for all k, all n greater than or equal to 1, there exists little n bigger than n such that t power n of x belongs to uk. So, in sum, that means the orbit of x intersects uk for all k. But the uk's form a basis for the topology, so the orbit of x is dense. And this set has full measure. So almost every point the orbit is dense. Is this okay? Just some set, follow what the sets are, it's not difficult. Okay, good. So let's do some examples of ergodic systems. So yeah, so in fact all the examples we've looked at are ergodic. So examples 1 to 4 are all ergodic. So let's try and prove some of them. So 1, I'll just give you a sketch of the proof. Okay? So R alpha, the irrational rotation is ergodic. So the idea of the proof is the following. Suppose you have a set which is invariant and which has positive measure. Okay? Then we want to show the measure is 1. So we can use something called the Lebesgue differentiation theorem for measures in Rn. Have any of you seen this? Or Lebesgue density theorem? No. It says that almost every point of the set A is going to be a point of density. So a point of density means you take x, so let x in A be a point of density of A. What does this mean? This means if I look at an interval around x, okay, so say x minus epsilon to x plus epsilon, and I look at the proportion of the set A which is in this interval. Okay, the proportion means I look at A intersect this interval. Okay, so look at A intersect this interval. I take the measure of that set and then divide by the measure of the interval. Okay? Then this ratio goes to 1. Then we say that x is a point of density of the set. Okay, that's what it means is that if I take a small enough interval, then A is going to fill up most of that small interval. Right? The measure of the proportion of A inside that interval is going to be close to 1. Okay. So this tends to 1. So as epsilon tends to 0. Okay, so Lebesgue's density theorem or Lebesgue's differentiation theorem says that almost every point of A is a point of density. So in particular there exists, since A has positive measure, there exists a point of density. Okay. So take a point of density. Now what can we do? We are allowed to choose epsilon nicely. So we can choose epsilon so that, and we're taking a rotation, right? So we know that high powers of this rotation are going to become small rotations, right? Yes? That's what we saw in the proof of minimality of the rotation. If I took a high power, then that gave me a small rotation. Okay? So I'm going to take some, let's say, R alpha power some large Q. Okay? And note that, of course, if the set is invariant under, my T is R alpha here, then it's also invariant under any power of R alpha. So what we can do is choose a small interval so that this iterate R alpha power q maps one endpoint to the other endpoint. So now apply my transformation here to this small interval. So what you're going to get is something like a tiling, okay? By intervals of length 2 epsilon, and then you'll have one small piece here which is of length less than 2 epsilon. It doesn't close up exactly. You'll have one small piece, but this has small measure. But now look, my set A is invariant, so and my map is measure preserving, so it's going to preserve the proportion of A in each of these small intervals. So suppose this ratio, the density of A is, let's say, 99% in this interval, then it's also going to be 99% in all of these intervals. So if you have 99% in each interval, then clearly in the union of these intervals you also have 99%, right? What's left is some small thing of some small 2 epsilon. So you'll have 0.99 minus 2 epsilon measure in the whole space. That's it. Okay. So we can do the same thing for the expanding map, for the angle doubling map. So do the same thing. Again, choose a point of density. So you let J be, say, x minus epsilon to x plus epsilon, right? And then, so density in J of A is, let's say, greater than 99%. And so when you apply the map T, in this case what happens? You know that after some time T power n of J is going to be all of S1, and again the angle doubling map preserves the density in the set. So if I have density 99% in this, I'll also have density 99% in the image under T. So here T of Z is Z squared. Okay. It's going to preserve the density. So therefore this implies that density of A in S1 is greater than or equal to 99%. The density stays the same. So that's the proof for ergodicity of the expanding. Is this clear? Yeah, we've shown that if you have a set of positive measure, you take a point of density, apply the dynamics, what you find is that the measure of A is almost 1. It's close to 1. As close to 1 as we want. So these two are ergodic. And now in the remaining time, I want to talk about ergodicity of the hyperbolic linear map. Right? Example 4. This is a nice argument, but I'll need some preparation for it. So all right, let's carry on. So here's a proposition. So the setup is we have a measure preserving transformation. So then the following are equivalent. T is ergodic. Then so Ergodic says if you have an invariant set, then its measure is 0 or 1. But it will turn out to be useful to have a slightly, I guess, stronger or weaker condition. weaker condition, which says that if a set is almost invariant, so almost invariant means that the measure of T inverse A symmetric difference with A is 0. So let me recall for you what the symmetric difference is. It's the part of two sets which is outside the intersection. So A symmetric difference B is A minus B, disjoint union B minus A. So it's, yeah, so saying that the symmetric difference has measure 0 says that the set is almost invariant. So if this is 0, then again the same A, measure of A is 0 or 1. Okay. Now third condition, this is going to be very similar to topological transitivity. It says if measure of A, you take two sets of positive measure, then there exists n such that measure of A intersect T power minus n B is positive. So this is like topological transitivity, okay? But it's a measure theoretic version. So this is also equivalent to ergodicity. And 4, if f from x to r is measurable function, which is essentially T invariant, that means f compose T is equal to f almost everywhere, then f is constant almost everywhere. Okay, and the fifth part is the same as the fourth, except you assume that f is in some LP space. So if f is in LP x mu, P1 to infinity, P any P. F compose T equal to f almost everywhere. That implies f equal to constant. So let's quickly run through the proofs of this.
So,
Yeah.
here in this Lebesgue density theorem,
Yes.
is it just the same as saying Radon-Nicotin derivative that restricted measure is almost everywhere 1 on or something?
So it does follow from Lebesgue differentiation theorem. Yeah. So Lebesgue differentiation theorem says basically if you have a function, so it's a version of fundamental theorem of calculus for measurable functions. So you take something like a function f. Well, here this is with respect to Lebesgue measure. You look at the integral over a set A, and then you divide by the measure of A.
Yeah.
Then if A is nice and goes to 0 in a nice way, this converges to f almost everywhere. So A really will be a sequence of sets based at some point x. So this goes to fx almost everywhere. So you apply this to the indicator function of the set A. So it follows from Lebesgue differentiation theorem. That's why I asked if you know Lebesgue differentiation theorem. Okay. So. Alright, so yeah, so let's quickly go through the proofs of this. So 1 implies 2. Yeah, this is not so trivial. This is not so trivial. So first of all, the claim is, so yeah, so all you have to prove is the following. Claim if mu of T inverse A symmetric difference A is 0, then there exists set B. So if you have an almost invariant set, then you can find the genuine invariant set. T inverse B is B, and the measure of B is the same as the measure of A. So proof of claim. So this will clearly prove that, this will prove 2, right? I mean, we have to show the measure of A is 0 or 1, but we are showing that measure of A is the same as measure of B, where B is T invariant. So we are assuming 1, which is T ergodic, so measure of B has to be 0. So we just have to prove this claim. So we want to construct an invariant set, so the natural thing is, invariant means that T inverse should belong to the set. So the natural thing to do is throw in all the pre-images of A, the inverse images of A. Now take the union n greater than or equal to n, and take the intersection, the same set we constructed before. So this is the set B. Okay? So then it's clear that this set is invariant. Now we have to show that this set has the same measure as A. That's the only sticky point. So measure of B is going to be, it's a decreasing intersection, so it's going to be the limit, capital N goes to infinity, measure of this union, n bigger than n. Okay? T power minus n. Now this is what? This is the same thing as the measure of a set is the same as the integral of the indicator function, right? Indicator of this set, of this union. Okay? Now let's look at this indicator function. So indicator of a union this is the same as the supremum of the indicator functions of the sets. So what's the indicator function of A union B? It's the maximum of indicator A, indicator B, right? So indicator of a countable union will be the supremum of the indicator functions. Yes? So we have to look at these functions. The claim is that this function is equal almost everywhere to the indicator function of A. So therefore its integral will be the same as the integral of A, which is measure of A. That's all. So we have to prove certain indicator functions are equal almost everywhere. Now we know that indicator of T inverse A symmetric difference A. So what is the indicator of the symmetric difference? It's going to be the absolute value of indicator T inverse A minus indicator A. But that's an easy thing to check. Yes? Just look at the Venn diagram, see where you are. There can only be 0 and 1, and they're going to be. Okay? So this fellow, we know this set has measure 0. So its indicator function is 0 almost everywhere. Right? Yes? A set has measure 0 if and only if its indicator function is 0 almost everywhere. So this is equal to 0 almost everywhere. That means on some set U such that measure of U is equal to 1. Okay? So what do we have? We get that. So indicator of T inverse A equal to indicator A on some good set U, some full measure set U. But the indicator of T inverse A is the same as the indicator of A composed with T. So this means that indicator of A composed with T is equal to indicator of A on U. Okay, U is a full measure set. So now we just keep playing with this game. So if some t power n of x belongs to U, then we have this relation. So indicator A of t of t power nx is equal to indicator A of t power nx. So indicator A composed t power n plus 1 x equal to indicator A composed t power n if t power nx belongs to U. So so if we look at the set U prime, which is the intersection of t power minus n of U over all n, okay, then first of all the measure of U prime is 1 because U has measure 1, so all its inverse images have measure 1. So intersection of measure 1 sets has measure 1. Okay. So then if x belongs to U prime, so U prime is our new measure 1 set, then t power nx belongs to U for all n, which implies that indicator A composed with t power n plus 1 x is equal to indicator A composed with t power nx for all n. So now you have this for all n. So this implies that you can, so this is for n, do the same thing for n minus 1. This will be equal to indicator A composed t power minus nx dot dot dots equal to indicator A. Right? You just keep applying this same thing n times. So that means all these indicator A composed t power n is equal to indicator A on this set U prime. So therefore this implies that this supremum over indicator of t power minus n A n greater than or equal to n. So this is the same thing as sup over n greater than or equal to n indicator A composed t power n. This, all of these functions are equal to indicator A on this set U prime. So the supremum is equal to indicator A on U prime. So that's it. So that means this function is equal almost everywhere to indicator A. So its integral is the same as integral of indicator A, which is mu of A. Okay? A bit messy, but not difficult. Okay, good. So now we can do, we are not going to prove 3. So we'll prove 1, 2, 4, 5 are equivalent. So 2 implies 4. Yeah, now, so given f measurable such that f composed t is equal to f almost everywhere, we want to show that f is equal to a constant almost everywhere. So what we can do is the following: for n greater than or equal to 1 and k an integer, let A n sub k be the set of x such that fx belongs to the interval k over 2 to the n up to k plus 1 over 2 to the n. Okay. Then, because f is almost t invariant, this set is going to be essentially t invariant. Okay, so then that's an easy thing you can see. F compose t equal to f almost everywhere implies that mu of t inverse A and k, symmetric difference A and k equal to 0. This you can check. So therefore each of these sets has measure either 0 or 1 by 2, right? But all these sets are disjoint. We are taking the inverse images under F of disjoint intervals in R, whose union is all of R, right? I'm just taking these intervals of length 1 over 2 to be. Right? So the A and K's are disjoint. Each of them has measure 0 or 1, and the total measure is 1. So there has to be a unique one which has measure 1. All the others have to have measure 0. Right? Yes, if you have numbers which add up to 1, all of them are either 0 or 1. Only one of them is going to be 1. Right? Otherwise you'll have 2 or 3, something bigger than 1. So there will be a unique one whose measure is 1. So take that one. Okay, so let me write that. So by 2, measure of A and K is 0 or 1 for all K, and disjoint union over K and Z of A and K is equal to X. Implies for each n greater than or equal to 1, there exists a unique K sub n such that measure of A n comma K n is 1. Right? And now we're done because we look at A, which is the intersection over n of A n comma K n. Then of course this is an intersection of measure 1 set, so it has measure 1. And this intersection is what? We're taking basically inverse images of intervals whose lengths are shrinking by half each time, right? So the intersection is going to be inverse image of a point. Okay, so this is A is going to be F inverse of some C for some C in R. What we'll get is a nested sequence of intervals which shrink down to a point. We're taking inverse image of that. So that means F inverse of a point has measure 1. That means F is equal to that point on a full measure set. So F is constant also. Okay, so that's 2 implies 4. Now 4 implies 5, thankfully, is trivial. Yes? You know it for all measurable functions, you know it for all LP functions. So 4 implies 5 is trivial. And 5 implies 1. Or will it be 5 implies 2? No, 5 implies 1. Yeah, so we have to show T is ergodic if every LP function is LP invariant function is constant. So if T inverse A is equal to A, then this means that indicator A compose T is equal to indicator A identically. But this means, and indicator A is a finite measures, I mean we are in a finite measure space, so indicator A belongs to LP. So therefore, by our hypothesis, indicator A is equal to constant almost everywhere. So if the indicator function is a constant almost everywhere, that means the set has to have measure 0 or 1. Okay, good. So we're carrying along. So that finishes the proof of these equivalences. So what we have to show is that all LP invariant functions are actually constant. So now it's time to state theorem which we will not prove. So this is the Birkhoff Ergodic theorem, which states the following: suppose T from x to x is measure preserving and f is an L1 function. Then we can look at what's called the forward time averages of the function f. So that I'm going to be calling f plus of x. So this is defined to be the limit capital N goes to infinity. So the time average along the of f along the orbit of x. So 1 over n, sum over little n goes from 0 to n minus 1, f of t power nx. So this exists, first of all, this time average exists for almost every x in x. Okay. I'm not assuming t is ergodic, just any measure preserving transformation. So the limit of forward time averages is going to exist. Moreover, f plus, so now it's defined almost everywhere. So it makes sense as a measurable function. So f plus actually will belong to L1 also. And f plus will be t invariant. F plus composed with t equal to f plus almost everywhere. That is something you would expect, right? If you compose with t, what are you doing? You're just taking the average over the orbit shifted by 1 time. So if you take the average over this and the average over this, then you would expect these two, the average should be the same, the limit. But anyway, this is what the theorem says. So you get a t invariant function in L1, and the integral of f plus d mu is equal to integral of f d mu. Okay, but we can say a bit more. So if our initial function f is actually in L2, so it's a stronger condition. Remember, for a finite measure space, L2 is contained inside L1. So this is a stronger condition. Then f plus is also in L2. And moreover, you can give an explicit formula for f plus. F plus is equal to nothing but, so L2 is a Hilbert space, so F plus equals the orthogonal projection of F onto the subspace, let me call it V sub T. So this is the subspace, it's a closed subspace of L2, say phi in L2, such that phi compose T equal to phi. So this second statement is actually called the von Neumann ergodic theorem. This was proved before the Birkhoff ergodic theorem, and the proof is much easier, it's much softer. Birkhoff ergodic theorem, the proof is definitely much harder. Anyway, so F plus becomes an orthogonal projection onto a subspace of T invariant functions. Finally, I want to say if T is invertible, so that means T has a measurable inverse, okay? Then you can look at F minus, so the backward time averages, F minus of x, which is the limit capital N goes to infinity, 1 over n, sum n goes from 0 to n minus 1, f of t power minus little n x. This is the backward time averages. Then this exists almost everywhere. And f minus is equal to f plus almost everywhere. So the forward and backward time averages for an invertible measure preserving map are equal almost everywhere. So, running out of time, let me try and say a few things quickly. So, let me give you a corollary of what this means. So, two corollaries. So, corollary 1 says that if T is ergodic, then f plus is equal to integral f t mu almost everywhere. Because if T is ergodic, then we know that f plus is an L1 T invariant function, so it has to be almost constant almost everywhere. But we know the total integral is the same as the integral of f, so the constant has to be integral f. Okay? So what is this saying? This is saying that, in other words, this is the way, this is the catchphrase, that time averages agree with the space average for an ergodic. Transformation. Okay. Alright. So now second corollary which we want to use is the following. So yeah, so if x is let's say locally compact separable metric space, then suppose we know that for all f which are continuous on x with compact support, so C sub C means continuous with compact support. Compact support means 0 outside a compact set. So suppose for all f in CCX we know that f plus is a constant almost everywhere, then T is ergodic. So proof is very simple. Note, so given f in L2, we know that continuous functions with compact support for a locally compact separable metric space, these continuous functions with compact support will be dense in L2. So there exists Fn in CCX such that Fn converges to F in L2. Okay?
So what's in the statement, where is, how is F related to T? F is T invariant.
No. Suppose that for all F continuous functions with compact support,
Okay.
the function F plus
Oh, I
which
see, I
we
see.
get
Okay,
from
okay.
Birkhoff ergodic theorem is a constant. The limit of time averages.
I see.
Okay. Then, so if we know, so see, our characterization of ergodicity number 5 said that if we know every L2 function, invariant L2 function is constant, then T is ergodic, right? So now all I'm saying is that we don't need to check it for all, it's sort of a converse, right? We don't have to check it for all L2 functions. If we know for continuous with compact support that the f plus, this is a T invariant function, is constant, then we are done. Then T is ergodic. And how do we see that? Because, so given f an L2 function, so choose fn's which converge to f in L2. Okay. Now, if P is equal to orthogonal projection onto L2, onto this subspace Vt, right? Then P is continuous, right? Any orthogonal projection onto a closed subspace is a continuous map from the Hilbert space to itself. So P of Fn, so what is Fn plus? This is nothing but P of Fn, right, by the Birkhoff ergodic theorem. And this converges to P of F, which is F plus. But these are constants almost everywhere, right? So this implies that F plus is, so this implies that Pf, which is F plus, is equal to constant almost everywhere. So that means the range of this orthogonal projection, i.e. Vt, is nothing but the constant functions. But this is just condition 5, that all L2 invariant functions are constant. So that's it. Okay, so 3:30, let's stop here.